Okay, let's now talk about logic microoperations. Again, these are very simple. Logic microoperations, they specify binary operations that can be performed on strings of bits stored in the registers. These operations, they consider each bit of the register separately and treat them as a binary variable. So they work bit by bit. That's why they're sometimes called bitwise operations, because they will not consider the entire contents of the register as a whole. They will consider them bit by bit. So if we have a register, 4-bit registers, and we have to add them, one of the registers has the value 8 and one of the registers has the value 7. So it won't treat them as 8 and 7. It will treat them as their bits and then add the bits. Okay, for example, the XOR micro operation. Uh, Very simple way to denote it. If p is equal to 1, when p is equal to 1, contents of R1 and R2 will be XORed and replaced in R1. So basically what you're doing is the contents of R1 will be replaced because R1 is the source register and R1 is also the destination register. So whatever the contents of R1, they will be XORed with the contents of R2 and R1 will be rewritten with this new value. So something like this, right? So what this thing symbolizes is, suppose this is R0, R1 and this is R2. The contents of R1 after performing this operation, given that P is 1, will be the result of the XOR of these. And this is what an example of a logical micro operation is. All other logic micro operations are like this. They work bit by bit, right? These are all the logic micro operations that are possible within a computer system. We have clear function, we have logical AND, we have logical OR, we have logical NAND, NOR, exclusive OR, exclusive NOR. We have complements, complement of one register, complement of another register. We can simply transfer the contents, right? We can set all the values of a register to ones and we can clear them. These are all the logic micro operations. Again, very, very simple. Here's an important note for you. See, this symbol plus, if you've been paying attention, you see this symbol plus can occur in two locations. When the symbol plus occurs in a micro operation, it denotes an arithmetic plus, like a simple mathematical plus. But when it occurs in a control function, it denotes an OR operation, right? In Boolean, it means OR. And here's an example to just illustrate that point. Now remember, the part of this statement before the colon is the control function. Everything before the colon is the control function, and after that is the register transfer statement. So this is the micro operation part, and this is the control statement. So what I mean to say is, when the symbol plus occurs in the micro operation like it does here, it means add. It means simple arithmetic add. But when it occurs in the control statement, which is the part of the statement before the colon sign, then it means, then it has a Boolean meaning, which is OR. So here, this plus denotes OR, which means if either P or Q are 1, then do this thing, right? If either P or Q are 1, then perform this operation. Uh, in case of this symbol, now there should be no confusion in this. If plus represents OR in the Boolean sense, then this represents OR within the micro operation, because we need to have a symbol for OR in micro operations as well, right? So the only confusion sometimes that occurs is between this plus sign. So whenever it is in the control function, that is the part of the statement before the colon, then it means OR. But in the rest of the statement, it means simple mathematical add. Now, returning to our previous conversation, see, there are 16 total logic micro operations, these ones. But most computers use only 4 of them, which is AND, OR, XOR, and complement. because from these four basic logic micro operations, all others can be derived. And this is the circuit that will allow you to perform all these four basic logic micro operations. All others can be simply derived by various combinations of these, right? Now, since this is the multiplexer, you know everything is going to be controlled by the selection lines. So when S1 and S0, both of them are 0, this entire circuit performs the AND operation. When S1 is 0 and S0 is 1, this entire circuit performs the OR operation, and you can check them. You can take any random values for A and B, and you can select one of any of these four sets of combinations, and you can see that the circuit will behave as mentioned in this function table, right? For 1 0 it will perform the XOR operation, and for 1 1 it will perform the complement operation, right? In case of 1 1 it only needs a one input from you, not two. So this logic circuit will be able to perform the four basic logic operations, micro operations that are required, and all others can be simply derived from these. Here are some applications of logic micro operations, just simple examples to show you what can be done with logic micro operations. See, logic micro operations, because they are bitwise, they operate on single bits at a time. They are very useful for manipulating individual bits or portions of a word stored in a register. If you don't want to mess up with the entire data stored in a register, if you only want to work with specific bits, if you only want to change specific bits, then logic micro operations come in very handy. For example, there's a logic micro operation of selective set. So selective set operation, what this does is, this operation will set to 1 the bits in register A where there are corresponding ones in register B, right? For example, suppose this is register A, 1010, and this is the register B, 1100. When we perform the selective set operation, it will be performed on A, and all those bits of A will be turned into 1 where there is a 1 in the corresponding location in B, right? So here we can see both the first bits, the zeroth bits, they are both 0, so it doesn't change, it remains the same. This is 1, and in the corresponding location in B register there's a 0, so nothing happens, it still remains 1. This bit in A was 0, in the corresponding location in B it was 1, so now this has been turned into 1. And this was 1 in A, and the corresponding bit in B was also 1, so again nothing happens, so it remains the same. So this bit and this bit of A remain the same, but this bit changes because corresponding to this bit there was a 1 in the other register. So whenever you want to specifically change certain bits, you can selective selective set them using a register whose bits are also 1 in those corresponding locations. So it doesn't matter what the bits of A are, if there is a 1 in the other register in that corresponding location, the bits of A will be turned into 1. So your selective set, why we call it set is because setting means making something 1 and unset means making something 0. So when we say set, we mean we want to make it 1, we want to make the bit 1, so that's why it's called selective set. You're selectively making some of the bits of a given register 1. Then we have selective complement. This operation complements the bits in A where there are corresponding ones in the B. Again, we have two registers A and B. This is the register that we want to change. We want to selectively change some of the bits of this register, 1010, and we are selective complementing it with 1100. So wherever, in whatever corresponding location there is a 1 in B, that corresponding bit in A will become 0. See, so the first bit, nothing happens to this because they're both 0. Then there's 1 and there's 0. So 0 doesn't do anything. Uh, the bit remains the same, 1. Then it is 0. This bit in A is 0, but in B it's 1. So now it will be complemented. It will be complemented. Whatever it was, it will be opposite of that. So 0 is turned into 1, and this one is 1, and again there is a 1 in B, so it will be complemented. It will become 0. So whenever you want to selectively complement certain bits of a register, you take another register and place ones in those corresponding locations which you want to turn into complements, and then simply take the selective complement operation with that register, and any location where there is a 1 in this B register, uh, those corresponding bits in the A register will be complemented. If they are 0, they'll become 1. If they're 1, they'll become 0. Then we have a selective clear operation. This is the exact opposite of the complement of selective set operation, because in that case we were setting the bits to 1. Now we are clearing the bits to 0, but only where there is a corresponding 1 in B. So I'm leaving this part for you to understand. And again, all of these micro operations, all of these can be simply written in register transfer language as well. You can replace the previous ones in this format also if you choose. Then we have the clear operation. This operation compares the words in A and B, the data in A and B, and produces an all zero result if the two numbers are equal. So basically, this is the XOR operation. This is what XOR does. When two numbers are the same, it produces 0, right? So we have two registers, A and B, both have the same contents, and through the use of the clear operation, we have cleared this entire register, all zeros. Now let's move on to shift micro operations. Uh, Shift micro operations are used for serial transfer of data. Now the contents of a register can be shifted either to the left or to the right, and there are three types of shifts that we can do. We can do logical shifts, we can do circular shifts, and we can do arithmetic shifts. So shifting is important, and it sometimes gets confusing, but it's very simple if you just pay a little bit of attention. A logical shift transfers 0 through the serial input. For example, if we write this micro operation R1 shift left, right, it indicates a 1 bit shift to the left of the contents of register R1, right? The contents of R1 will be shifted left once, and those shifted contents will then be moved into R1. If we say shift right, then the contents of R2 will be shifted right by 1 bit, and those right shifted contents will be moved into R2. Here's an example of a logical shift left. So this is a register R1. Its contents are 100, 11, 1, and we are supposed to shift it left by 1 bit. How it works is you simply shift this entire string of bits 1 bit to the left and drop the leftmost bit. Drop the leftmost bit, and all the other bits are shifted 1 bit to the left, and then in the end we have a 7-bit number, but we needed 8 bits, right? So we add an extra 0 at the end. So we shifted the entire register 1 bit to the left. This leftmost bit had to be discarded, and in the end we are left with 1 less bit because we discarded 1 bit. So in place of that we just write a 0. So this is what R1 becomes after logical shift left by 1 bit. Same way you can do it by 2 bits, by 3 bits, by 4 bits. It all depends on how many leftmost bits you'll have to discard and how many zeros you'll have to add to make up for the ones that you discarded. This is what logical shift left is. This is an example of a logical shift right. Now, in this case, what you're doing is you're taking the string of numbers 100, 11001, 8-bit numbers, and you're shifting all of them to the right, discarding the rightmost bit this time. And after shifting the numbers, you'll have one bit less because you discarded one bit, so you add 0 to the left. In this case, we added 0 to the right and discarded the leftmost bit. In this case, we are discarding the rightmost bit and adding 0 to the left. That's a logical shift right. And you can do that as many times as you want. It will all depend on how many rightmost bits you discard and how many uh, zeros you add to the left, right? So you can see the flow of the left shift and the right shift. And this flow is important to see, right? Then we have circular shift, also known as a rotation operation. Circular shift circulates the bits of the registers around the two ends without loss of information. So you see, in case of shift left and shift right, we were discarding some bits. We were discarding the leftmost bits or we were discarding the rightmost bits. In case of a circular shift, you can assume that the register is like a tube which is connected. The two ends are connected to one another, right? Like a circle. So nothing gets discarded. Whatever you discard from one side gets placed in the other side. So, for example, in logical shift right, we discarded this and added 0. In that case, what would happen is this one will go here. So you don't have to waste this one and add a 0. You just simply remove it from this point and add it to this point. So it's like a loop. That's what circular shifting is, right? And this is the nomenclature, this is the symbolic notation for circular shifting. This is circular shift left, this is circular shift right. And these are examples of circular shift. So again, we have a register with 8 bits, 100, 11001, and we are supposed to circular shift left, perform circular shift left. Now in left shifting, if you remember, just perform your simple left shifting. Shift all the bits to the left, discard this one, right? Shift all the bits to the left, and then you're one bit less, one bit short. So you move whatever you discarded, place it at the end. So instead of adding a 0 here, like we normally do, we just repurpose this bit that we removed in the shifting process. So it becomes the circular shift. Circular shift right is also the same way, right? This is the one that you were going to drop. This is the rightmost bit that you were going to drop. And instead of dropping it and putting a 0 here, you are simply just repurposing it and putting it back here, right? Okay. Then we have arithmetic shift. This shifting is for signed binary numbers. Signed binary numbers can be shifted to the left or the right. And it's very important to note that this is for signed binary numbers because otherwise it gives incorrect results. The micro operation for arithmetic shifting is like this: arithmetic shift left, arithmetic shift right. Another purpose of arithmetic shifting is arithmetic shift left actually multiplies a signed binary number by 2, and arithmetic shift right divides a signed binary number by 2, right? And the important part is the sign bit. Sign bit is the leftmost bit. It must remain unchanged. Otherwise, what would it mean for the sign bit to change? Negative number is becoming positive upon shifting, and positive number is becoming negative on shifting, which shouldn't be, right? If your shifting is basically multiplication and division as far as arithmetic shifting is concerned. So if you're multiplying a number by 2, for example, why should the sign change, right? If you're dividing a negative number by 2, it should still be a negative number. If you're multiplying a positive number by 4, it should still be a positive number. So it's very important to note that in arithmetic shifting, first of all, it's for signed binary numbers. Second of all, it's corresponding to multiplication and division. And third, the sign bit should not change. Now, this is what arithmetic shift right is. Let's first start with right. Now, like I mentioned, the sign bit should not change. So it's going to be exactly like your logical shift right. You're going to shift all the numbers to the right and then drop one number. But in this case, the only difference is since the sign is not supposed to be changed. So the extreme left bit, which is your sign bit, should remain the same. See, this is R1 again from the previous examples, and this is a negative number because it starts with the 1. After shifting, it should still be a negative number, right? So, first thing we do is we copy this first bit, the leftmost bit, as it is, and then we shift this entire number. So, instead of thinking about it as shifting it, an easy trick for you is first you copy this same number as it is, and then you copy this entire number after it, right? And then since you have 9 bits and you wanted 8 bits, you just drop one of the bits, right? So first you copy the first bit as it is because the sign should not change, and then you copy this entire number again, 8 bits, you copy them. This will be the result you get. And then since you only need 8 bits, right, you discard this one, and that is arithmetic shift right. Now this is arithmetic shift left. Now in this case, what's happening is this one is exactly like logical shift left. Exactly like logical shift left. There is no difference. You can compare this slide with logical shift left slide and there will be no difference. Now what's happening in this case is we have been lucky because our sign isn't changing after shifting. We have dropped this, we have added an extra 0. That this part is fine, but dropping of the bit is quite significant because if this number was 100110001 instead of 110110001, then by dropping this, the first number here would have been 0. If we are shifting 10110, for example, so it would have been 01100. What's happening is negative number is turning into positive number, which is wrong, right? So in arithmetic shift left, a problem occurs which is called overflow. And this is what overflow is. Arithmetic shift left can cause the sign bit to be lost, which means that a number which was originally negative or positive could become positive or negative after the shift. So this will generate an erroneous result, right? And remember, this is for signed numbers, and we are doing this so that we can perform multiplication and division. And because of multiplication and division, the sign should not change. But in arithmetic shift left, and only in arithmetic shift left, there is no problem in arithmetic shift right. Arithmetic shift right works perfectly. But in arithmetic shift left, because it works exactly like logic shift left, the leftmost bit is discarded. And that means the sign can change. And the changing of the sign is known as overflow. If, uh, if after performing arithmetic shift left, um, a positive number becomes a negative number or a negative number becomes positive number, then we say that overflow has happened. For example, if this was our original number, which you can see is negative, and then we shifted it left, this is arithmetic shift left by 1 bit. So this will be dropped 00110010, right? But this is now a positive number. So this is an overflow condition, which is a problem with arithmetic shift left. All right, let's get into some exercises now. Okay, let's start with this one. Show the block diagram of the hardware that implements the following register transfer statement. It's very simple, a simple control statement and register transfer statement. Now, what we need to do in these types of questions is, first of all, identify all the components that we are going to use. So we can see that we have registers, we have R1 and R2, we have two registers, and then the control is going to be made up of two parts, Y and T2. All right, and this is Y and T2. So let's see, this is what it's going to look like. The basic components remain the same. We have the two registers R1 and R2, right? R1, uh, some data is being transferred from R1 to R2. Since we don't have the knowledge of what this is, how many bits are being transferred, we can just assume that they are n bits, right? Because we only need a symbolic representation for this. So n bits are being transferred from R1 to R2 and then back from R2 to R1. So we can draw them. From R1 to R2, n bits are being transferred, and then from R2 to R1 back, n bits are being transferred. If you want, we can take them out as well, depending on what the situation is. We need a clock. As I told you, clock is a very important component, and whenever registers are being loaded with information, because in this case both registers are at one time, R2 is the receiving register, and at one time R1 is the receiving register. So both of them, since both of them are going to be receiving some information, they both need clock. So the second thing you do is draw the clock. The third thing is your load, your control statement, which is directly given to you. All you have to do is use the appropriate gate for Y and T2, and you get both of them together will control the loading of your registers. And that completes the hardware that implements the given register transfer statement. Simple enough. First, you did words, identify the main components, which were the two registers, and see which of those registers are the receiving registers. Both of them are the receiving registers, so both of them have to get the clock. And then you need the control circuit. So control circuit is given to you. You just have to use the appropriate logic gate, and then you're all set, right? This will control the loading of both the registers. Or you draw the appropriate circuits, you complete it, and that's it. Okay. Represent the following conditional control statement by two register transfer statements with control function. So this is a conditional control statement, and we encountered something like this in this video earlier as well. So this is a conditional control statement, and we need to convert it into two register transfer statements with control functions. And to find the control functions, it's very, very simple. All you have to see is, see, it says if P is equal to 1, then do something. Else if Q is equal to 1, then do something, right? So P and Q are therefore the control elements. These are the control functions. So we can write it like this. If P is 1, if P is 1, transfer the contents of R2 into R1. So this is fine. But the second part of it says, else if Q is 1. So P is not 1, but Q is 1, then transfer the contents of R3 into R1. So here goes the second statement. And this is all you had to do. Simple enough? Alright. So a digital computer has a common bus system for 16 registers of 32 bits each. So number of registers is 16. Size of each register is 32 bits. The bus is constructed using multiplexers. Three questions that follow are: what size of multiplexers are needed? How many selection inputs will there be in each multiplexer? And how many multiplexers will there be in the bus system? And all of these three questions can be answered by knowing two things: how many registers there are, and what's the size of the registers. Okay, so the first part, what size of multiplexers are needed? See, we have 16 registers. If you recall the diagram for the common bus system, you'll see that the size of the register depends on the total number of registers. In that example, we had 4 by 1 multiplexers because we had 4 registers. So we have 16 registers now. So the size of the multiplexer will be 16 by 1. How many selection inputs are there? So this one is simple because if the size of the multiplexer is 16 and 2 raised to power 4 is 16, so there will be 4 selection lines. Again, this is a callback to multiplexers, so if you recall those concepts, this will be easier for you to grasp. And finally, how many multiplexers are there in the bus system? Recall from our example that uh, we had as many multiplexers as there were bits in the registers. The size of the register controlled the number of the multiplexers to be used. So in this case, the multiplexers will be 32 because we have the registers are of size 32 bits. So 32 multiplexes, one for each bit of the registers. So 16 by 1 multiplexes with 4 selection lines and 32 total multiplexes. Question 4. The following transfer statements specify a memory. In all of these, you see there's a memory specified. Explain the memory operation in each case. This is again very simple. Let's take a look at it. The first one. The first one says read the memory word specified by the address in the address register. Read the word specified by the address in the address register and read it into R2. Transfer it into R2. The second one says, now see, in this case, it's easy to see that this is a read operation because something is moving from memory into a register. In this case, something is moving from a register into a memory. That means it's a writing process. You're writing something. So write the contents of register R3 into the memory word which is specified by the address in the address register. There's going to be an address in the address register. It will point to a specific memory location. Put the contents of R3 in that memory location. Finally, read the memory word specified by the address in R5. Now the address is not present in an address register but rather in another general register R5. So read the word specified by the address present in R5 and move that or transfer that into R5. So naturally R5 first contained the address. Now it will contain the actual value present in that address location. So the contents of R5 will be overwritten. Next question. Draw a block diagram of the hardware that implements the following register transfer statement. So this is the register transfer statement. Again, very simple. AR and BR are two n-bit registers. XYZ are the control variables. We have to include the logic gates for the control functions, obviously. You have to remember that a plus sign denotes an OR operation. See, I told you this. Plus sign denotes an OR operation in the control function, but it represents an arithmetic operation inside the micro operation. Now, again, for these kinds of questions, like we just discussed, what you have to do is first of all identify all the components that you have to draw. So, what are the registers here? AR and BR. So, we can draw the AR and we can draw the BR. And since they're supposed to be added, so we need an n-bit register because it's mentioned that they are n-bit registers. So add an n-bit adder that is capable of performing AR plus BR. We need to do AR plus BR, which will be done through an n-bit adder, right? The contents will be moved into AR. What's important to note is this part, the control. How do we draw the control? Let's first uh, make all the transitions of the data value, right? So n bit of data value will go into the n bit adder from BR, and n bit of data value will go into the n bit adder from AR. AR and BR to be added, right? So the contents of AR will move into the adder, the contents of BR will be moved into the adder, and the result is supposed to be stored back in AR, right? The sum is supposed to be stored back in AR from where it is supposed to be taken out. So all these lines are now drawn. And simply, all of this is this, right? X or Y and Z. X or Y and Z. This is simply the load, and then the register that will be taking the input will have the clock. So it has the clock, and we are done. That's all we had to do. That was simple enough, right? Okay. Show the hardware that implements the following statement. Again, a similar question. In this case, you can see that the micro operation is quite simple, but the control statement is quite lengthy. So you have to include the logic gates of the control function and a block diagram for the binary counter with a count enable input. Where does the binary counter come in? You might be wondering. See, this part, AR is AR plus 1, is essentially a binary counter, right? So, n bit binary counter with the clock. Remember the clock. Now, what we have to do is draw this, and it's very simple. First, we start with this part, x and y and t naught, right? And then y naught t2, y naught and t2, and then t1, right? And all of them have to be odd. So this one, and this one have to be odd, and this will be your load with count enable, and that's how you're supposed to do this. Again, very simple. All right, next question. The adder subtractor circuit shown below has the following values for the input mode M and data inputs A and B. Remember the adder subtractor? It acts as both an adder and a subtractor depending on what the value of mode M is. In each case, what we need to determine is the values of the outputs. So both A and B, the inputs are given, the modes are given. All you have to do is remember which mode stands for what and then perform the necessary computation, right? This is the adder subtractor in case you forgot. All right. And I think this is simple enough. When mode is 0, the circuit is supposed to act as an adder. And when mode is 1, the circuit is supposed to act as a subtractor. And the subtraction is very important. It's performed in 2's complement form. So whenever the mode is 0, like in this case, all you have to do is simply add A and B, add A and B. This is the sum, this is the carry. Make a note of all of these. This is the sum, this is the carry. When M is 1, this is supposed to be a subtractor, right? So we have to do A minus B. We have to do A minus B. That means B is supposed to be in the 2's complement form. So A, this is minus B, right? And whatever you have at that point, in that case it's called borrow. Basically what you're doing is you're adding 2's complement, so the terminology still remains carry. It's still called carry, even though in subtraction it's supposed to be called borrow. But if you think about it, what we're doing is adding 2's complement. So 2's complement is a negative number. We are adding a negative number to it. So essentially we're performing subtraction, but technically we're performing addition of a negative number. So anyway, no need to get confused in this. What we need to do is we take A and subtract the B's 2's complement from it, get the result, and keep a track of the carry. That's all you had to do in this question. Again, all you have to do is remember what m is equal to 0 and what m is equal to 1 stand for. Now, register A holds the 8-bit binary 110110001. Determine the logic microoperation and the value in the second register B that will cause the value in A to be changed to this and to this. Now, in this question, the thing is you need to employ some good guessing, some educated guessing, because we have been given A and B is a question mark, so that C becomes this. So we need to do A and then some operation B on it, which gives us this one, this number, and then it gives us this number. Two separate times we have to do this. And through some hit and trial, you'll note that the first result you can get through an XOR operation, right? XOR operation with B and OR operation with this B will give you the second number. So A remains the same. You have to guess the operation and the second register B. That will give you these results. All right. The 8-bit registers AR, BR, CR, and DR initially have these values. Determine the 8-bit values in each register after the execution of the following sequence of micro operations. Very simple. All the registers are given to you. These micro operations you have to perform on these values and find out what the final values are. So, for example, you can start with the first one, AR plus BR. We are supposed to add AR and BR and then tell what the values of the final four registers are, right? You can do this AR, BR, bitwise, you add them, and finally you mention what all the registers are. Same goes for the second one. In this case, what you have to do is you have to perform this operation and then you have to perform increment also. So and also you have to perform and then increment, and then finally tell what the four registers are. And in this one you have to subtract. So subtraction is done through 2's complement. So take the 2's complement of CR and you'll get the result. This I'm leaving up to you. Okay. An 8-bit register contains the binary value 100111100. What is the register value after an arithmetic shift right? Arithmetic shift right. The first thing you have to do is perform arithmetic shift right on this number and find out what the value is. Now, starting from the initial value of this one, determine the register value after an arithmetic shift left and state whether there is an overflow. So you have to do two things. On the same number, you have to do arithmetic shift right and arithmetic shift left separately and see if there is an overflow. So this is the given number. After arithmetic shift right, if you recall how it's done, it will be this number, right? After arithmetic shift left, which works exactly like a logical shift left, you'll see that there's overflow because this number became this number upon shifting, and you had to drop the 1 because this is arithmetic shift left. So you had to drop the 1, which made this negative number into a positive number. So there has been an overflow. Okay. Now, starting from the initial value of a given register, determine the sequence of binary values in R after a logical shift left, followed by a circular shift right, followed by a logical shift right, and a circular shift left. That's all you have to do. On this given number, first perform logical shift left. On that number, then perform circular shift right. On that number, then perform logical shift right, and finally circular shift left and tell what the final result is, right? And you can see that this is what you'll get. This is after logical shift left, after circular shift right of this number, logical shift right of this number, and circular shift left of this number. I really like these kinds of questions where we have to find what's wrong with something because instead of your regular questions where you follow a normal linear forward pattern of thinking, a question is given and you're trying to find out the answer. In these types of questions, you something is given, a statement is given, and the idea is to find what's wrong with it. So you have to think in a different way. Anyway, so three statements are given to us, and the idea is to find what is wrong with each of them. So, what's happening in the first one? The complement of AR is being transferred into AR, and AR plus 1 is being transferred into AR when X and T are 1. In the second one, when Y and T are 1, The contents of R2 are being transferred into R1 and contents of R3 are being transferred into R1. When Z and T are 1, contents of AR are moved into your program counter and program counter is being incremented. So if you remember, I mentioned several times already that whenever um, a register control, sorry, a register transfer statement is given with a comma, separated by a comma in a single line, it means that these two operations are happening simultaneously. So now let's find out what's wrong with each of them. The first one, see, the contents of a register cannot be complemented and incremented at the same time. You can't complement AR and add 1 to AR at the same time. Similarly, two different values cannot be transferred into the same register at the same time. You cannot have both R2 and R3 going into R1 at the same time. At any given click, only one of these things can happen, right? Finally, it's not possible to move a new value into a register and increment that value at the same time. So you're moving something into the program counter and you're incrementing the program counter as well. You can do one thing. One has to wait, right? You can't add something to a register, put something into a register, and then increment the value of that register at the same time. So this is what is wrong with each of these statements. And with that, we have reached the conclusion, end of this video. So, just a quick recap. In this lecture, we talked about microoperations, register transfer language, register transfer, bus and memory transfer, and arithmetic, logical, and shift microoperations. We also solved some exercises. That's it for this video. Until we meet in the next one, bye bye and take care.